Okay, so this is Math 2414. This is January 22nd. A couple things I want to point out to those of you who are listening to me live today, and then also anybody who's watching the recording later. We will start doing homework this week. I'm doing homework two different ways. I'm giving you practice homework. That is homework you already have. I've posted on my Google site. So you have all the problems I'm going to be assigning from the textbook during the semester. Those are practice problems. That's ungraded homework. You don't turn that in. You can ask questions about it, certainly. If you have questions, you can ask during live lecture. You can ask during office hours. Jaime showed up at my office hours, I guess, last night, and we went over, I spent 30 minutes or 30 or 40 minutes. We talked about questions on the homework. So that's a good thing for all of you to be able to do. So take advantage of that when you have questions. Then the other part of the homework is I do have graded homework. That's going to be just a problem or two from each section, from each class period. I will assign that at the end of lecture each day. So I'll assign a problem or two at the end of class on Monday, the end of lecture on Monday, at the end of lecture on Wednesday. Both of those together will be due on the following Sunday by midnight. And you turn those in as a single PDF. There's lots of apps out there, and I talk about that on the Google site and in my syllabus. Lots of apps out there you can use to take your phone and turn it into a scanner, and you can scan documents in easily and make it into a single PDF. That's what I do require, is that two things about those homeworks when you turn them in, is that they be turned in as a single document, not as a bunch of separate documents or separate files, but just one file, and it's got to be a PDF. That way it's kind of uniform. And I think probably eventually I'm going to, and maybe later this week, I'm going to tell you a uniform way to name your file. That way everybody is named the same way, and I can keep it straight that way. At the bottom of my Google site, there's links, and there's already a few of them there, and you can go down there and click on the appropriate link for the appropriate due date, and you can turn in your document directly to my Dropbox. And when you turn it into my Dropbox, only I can see it. No one else can see it in there, because nobody else has permission to look at anything in that Dropbox except for me. So, and then I will post grades on those during the following week when I grade them. And what I'll do is, if you decide you want it back graded, you can always go on to D2L. I'm going to post your grades on the D2L gradebook. And if you want the graded assignment back, then you can email me and I'll just send you an electronic copy of it back. I will also probably post the solutions to those somewhere along the line during the following week, so that you have the worked out problems there available to you as well. So please let me know how things are going with homework. This is a little bit different than the way I did my calculus class in the fall. And so we're going to kind of see how this works out. So online office hours, don't hesitate to come by. I already mentioned this, but Sundays and Tuesdays, 8:30 to 9:30 at night, and then Tuesday, Wednesday, Thursday, 11 a.m. to noon. Exam 1 we're already beginning to think a little bit about Exam 1, even though we're really just started the semester. And the window for Exam 1 goes from February 8th through February the 13th. And I will be posting a review for that by January 31st, and that's just next week. So next week you get a review that'll be about a week ahead of the actual window for the Exam 1. And remember, you have to take the exams in a proctored testing center, so most of you are going to be taking them in the Lone Star College system. I do not care which college in the system you take the test at. You just need a photo ID, and I will get that back, the scanned copy of that test back, sent to me by that testing center. And I'll distribute the exams the same way I do homework. I'll post the grades on my D2L gradebook. You can go in and look at your grades. If you want a copy of your exam back, you simply email me and I'll shoot you back a graded copy of your exam. So it shouldn't be too big a deal. And that generally worked out pretty smoothly in the fall. All right, so today what we're going to do, our outline for the day today, is we're going to continue doing a little bit of reviewing for integration. I worked numerous problems at the beginning of class last time, and I'm going to work 3 problems this time. And each one of these problems is illustrating something specific that is something that I expect that you've seen back in Cal 1, but maybe it's something you've forgotten. Maybe it's possible you didn't cover it in Cal 1, then you need to go back over it again. But these are all illustrating integration skills that are going to be important to you as a Calculus 2 student, and then again for you as a Calculus 3 student as well. So I want to, I've kind of picked a couple of specific things I want to talk about and illustrate with some problems with integration. So I want to do that first, 2 or 3 problems, like I said. Then we're going to finish up area between 2 curves. We're going to look at probably 3 problems with the area between 2 curves. We did some work with that last time in class, but I definitely need to do more work with area between 2 curves. And then finally, we're going to do volumes of solids of revolution. We're going to talk about what a solid of revolution is, and then talk about the disk method and the washer method for finding volumes. And then on Wednesday of this week, we will look at a method called the shell method. So we'll do solids of revolution and volumes again on Wednesday, but we'll look at a different method for doing that that's applicable in other situations that maybe the disk method doesn't work so well on. And we'll look at a couple of animations during class today so that you can kind of visualize some stuff that we're doing also, because it's pretty visual what we're doing. So, all right, so with all of that in mind, does anybody have any questions before I get started? For you guys that are with me today, anybody have anything that they need to ask me about here at the beginning?
Yes, for the exam, do we have a time limit?
Jaime asked, probably some of you who are watching or listening to the recorded version wouldn't be able to hear his question, but he asked if there's going to be time limits on the exams. I think that was the question, right?
Yeah.
And this is the way I look at it is, yes, there is a time limit on the exam, but I usually set it at a time where everybody's going to be finished with the test. Before that, most likely, very few people would run into a time issue on the test. I'll usually set it at somewhere between 2 hours and 30 minutes and 3 hours. Most students should be able to finish the test in an hour and a half, hour and 15 minutes to an hour and a half. So you should have plenty of time to take the test, and that shouldn't be too big of an issue. So good question. I will put a time limit on it. But generally speaking, what I would do if I were you, for all of you who are taking my test this semester, is that allow yourself 3 hours to take it, just so in case something bizarre happens on the test and you hit a problem that you really struggle with, it gives you gives you a safety net as far as the time on the test goes. And so, pay attention to the time that the testing center you're going to use closes. So if it closes at 8 o'clock, you ought to start the test by 5 o'clock, maybe 5:15 at the latest, something like that. You need to give yourself at least 2 hours, 2.5 hours, or 3 hours to finish the test, just to make sure. So, all right. So any other questions anybody's got? Okay, it doesn't sound like there's any questions. So we are going to move on. We're going to first talk about integration, and a little bit going back over a little bit of different situations that come up with integration. So the first item I want to talk about, first skill I want to talk about, are integration problems where long division is helpful for the problem. All right, so this is an example of a problem where long division is helpful to evaluate this integral. X squared plus 3x plus 5 over x minus 2 dx. Now, remember that when you have a rational expression like this, when there's a polynomial in the numerator and a polynomial in the denominator, that one thing I told you to do last time, and this is true even if it's not a polynomial over a polynomial, is always check to see if you have du over u, right? See if you have a logarithm. And so like in this particular problem, clearly you don't. Remember that for when you have a fraction, always briefly check if you've got this form, du over u. And remember, du over u, in words, you're talking about having a function in the denominator and the derivative of the function in the numerator. And if you've got that form, the derivative of a function over the function like that, then remember that, then you've got a logarithm. Right, and so that's the log form right there. So always briefly check to see if you have du over u. Now that clearly doesn't apply in the problem that I've given you right here. When you see that the degree of the numerator is bigger than the degree of the denominator, if you have a fraction and it's a polynomial over a polynomial, right? So it's a rational. Remember that's called a rational expression in algebra. And if you have the degree of the numerator, I'm going to write degree and abbreviate numerator, is greater than or equal to the degree of the denominator. So either they're the same or the degree of the numerator is bigger, then a strategy to use is to try long division and see if that helps you rewrite the integral in a different form. See, so like in our problem that I'm talking about right here, the degree of the numerator is 2, right? And the degree of the denominator is 1. So the degree of the numerator is 2 and the degree of the denominator is 1. And so this is a case where long division ought to come up in your head when you see this polynomial or this integral and say, hey, maybe long division is going to help me in this problem. So what you do is you take x squared plus 3x plus 5 and you divide it by x minus 2. Now, there's all sorts of ways you could write out long division, and I'm not going to go through all the different ways. And a lot of you, if you went to school in Europe or if you went to school in certain parts of Asia or in Mexico, there's all sorts of different ways to write out long division. It's not a standard algorithm at all. And so I don't care how you write it out at all. That is absolutely, don't worry. I don't worry about that. So if you write it out differently than I do, not a problem at all, as long as you can divide it out. So this is what I do. I just take x squared plus 3x plus 5. I divide it by x minus 2. And then I take the x squared and I divide it by x. And that goes x times. And so the first term in my quotient is x. And then I multiply. And then remember what you do at this point with this algorithm is you subtract. So x squared minus x squared is 0, and 3x plus 2x, because you're subtracting negative 2x, is 5x. And so you have 5x plus 5. Then you go through the whole process again. You recycle and go through the whole thing again. So you take 5x and divide it by x, and you get 5. And so that's the next term of the quotient is 5. You multiply again, and you get 5x minus 10. And then you subtract. 5x minus 5x is 0. Remember, the first terms are always going to cancel out. And then 5 minus negative 10 is the same thing as 5 plus 10, or 15. And that's the remainder right there. And so remember, the way you write the quotient out is you write the quotient, which is x plus 5, and then you tack on the remainder. And remember, the way the remainder gets tacked on is it's 15 over the divisor. And so what you're saying is when you divide those two polynomials, that's your quotient right there, is x plus 5 plus 15 over x minus 2. See, and this helps hugely in this problem because the way the integral was originally written, there was no readily identifiable antiderivative, but now I've got these terms and I can find the antiderivatives for these terms really easily. The antiderivative for x is obviously 1/2 x squared. The antiderivative for 5 is 5x. And then on this last term, I'll go ahead and write it out as an integral just to kind of remind you here. The 15 is a constant. And so on this last term, really all you have is dx over x minus 2. See, and that's a logarithm because it's du over u. Right, that's in the form du over u right there because the derivative of x minus 2 is just 1. And so, so that's just a logarithm. And so this ends up being a really easy integral after you have gone ahead and done the long division. So this would be 15 times the natural log of the absolute value of x minus 2 plus c. Boom, and you got it. Right, so, but that would have been a difficult problem if you had not done the long division. And so you, in a problem like that where the degree of the numerator is bigger than or equal to the degree of the denominator, try long division and see what happens with the integral. And that's going to typically work in a situation like this. So remember, what I want you to do is if you're okay, then that's fine. If you have a question about something as we go through these, shout out, stop me, and we'll go back over it again. All right? All right, so long division, that was one thing I wanted to talk about. Second thing that I want to talk about with integrals that I want to remind you of is the idea that sometimes completing the square will change the way an integral looks and will allow you to match up an integral form easily. Completing the square especially comes up, this isn't the only time it comes up, but it especially comes up when you've got one of the inverse trig integrals. So, remember the forms are du over a squared plus u squared, which is 1 over a arctangent of u over a plus c. And then you have du over the square root of a squared minus u squared, which is just arcsine of u over a plus c. And then finally du over u times the square root of u squared minus a squared, which is is 1 over a arcsecant of u over a and then plus c. Now remember, I use the arc notation for inverse trig functions. You can use the inverse trig notation if you want to. I don't have a problem with that. But I exclusively use the arc notation when I'm doing inverse trig functions. So like arcsine of u over a, if you insist on writing this as inverse sine of u over a like that, I don't care. That's fine. If you're used to doing it that way, if that's the way you saw it in Cal 1 or in pre-Cal or wherever, that's not a problem. I just think the arc notation is a little bit more clear as far as the fact that you don't have an exponent in there, that you're talking about an inverse trig function there. All right, so let's talk about an example that fits one of these forms, but where we need completing the square to do the problem. Okay, so this is our example. As the integral is dx over the square root of 10x minus x squared. All right, so in this particular problem, if you're looking at those forms, the form that you would suspect, based on the way this integral is written, is the middle one. Is you kind of suspect the arcsine function, but the way it's written, you've got you don't have it in the form a squared minus u squared. Remember, a squared is just some constant, and then minus something else, some function squared. So but it is a quadratic expression under the radical, so this is one where completing the square would likely help you rewrite the integral. So what you do, and again, there's several ways I could write out completing the square, but this is what I'm going to do, is I'm first going to put the squared term first. Right, so I just rearrange the terms. You always want the squared term first. And then you also want the squared term to have a coefficient of positive 1. So you factor out a negative 1 out of these two terms right here like that. And then remember, the idea with completing the square is that what we're going to do is we're going to add in a constant to that quadratic, and the way you figure out that constant is you take half the middle coefficient and square it. So you're taking half of 10, which is 5, and then squaring it to get 25. And I certainly expect that all of you have completed the square and used that algebra technique somewhere in calculus or pre-calculus or algebra 2 or somewhere. All right, so what am I going to do? I'm going to take half of 10x, or half of 10 rather, which is 5, square it, and I get 25. So I'm adding 25 in here. All right, and like that. I close the parentheses off. But remember, I can't just add in a 25 in there, because when I just add in a 25, I've changed the integral. Now, I can't just add a number like that, because I'm changing the integral when I do that. And I don't want to change the integral. And so I've got to do something to offset the fact that I've put that plus 25 in there. And so we do the opposite outside of the parentheses, but underneath the radical. Now you have to be careful, because there's this -1, this pesky -1 is sitting there, and that -1 gets multiplied by the 25. Right, so -1 times 25 is -25. So what that means is I really haven't, and that is a -25 there. It didn't look like it, but let me put that in there again. Okay, so it doesn't look like you've subtracted 25, but you've really subtracted 25 there. And so when you do the opposite, you have to add 25 on the outside. And now I know it looks like you're adding 25 twice, but you're not. Because of that -1, that the 25 that's on the inside of the parentheses is really a -25. All right, so we're almost there. We've almost got this set up, right? So now we go ahead and factor. That's why you're doing this. And what I'm going to do is I'm going to take that 25 that I've added in at the end. I'll put that first, and then the minus sign, and then x squared minus 10x plus 25 factors x minus 5 squared. Boom, and I've completed the square. And notice then when you compare it to the form du over the square root of a squared minus u squared, it's starting to look like that form, where a is equal to 5, right, because a squared is 25, so a would be 5. U would be x minus 5, because that's the function that's being squared. And then du, remember du has to match up also. And remember, if u is x minus 5, then du is defined to be the derivative of x minus 5 dx. But the derivative of x minus 5 is just 1. So du is equal to dx. Boom, it fits that form exactly. It fits the arcsine form exactly. And so we can just write out the arcsine form here. And so we've got that it's going to be arcsine of u over a, and so this would be x minus 5 over 5. I'll put parentheses around that, plus c. And we've got it. We've got the antiderivative written down. But if you had not completed the square, there's no way you would have gotten that form. And so completing the square is definitely something that you'll use. The inverse trig functions are the most common places to see it when you're talking about integration. Not the only places, but the most common places. So definitely something that I wanted to mention to you and bring up again. And any questions there?
No, we're good.
All right, I think I think I'm hearing everybody's all right. Then the last little technique for integration that I want to mention is splitting an integral. That sometimes an integral is easier if you take it and split it into two integrals, into two pieces, essentially. So as an example of that, the integral will be, let me erase this here real quick. We're going to look at 2x plus 3 over x squared plus 16 dx. Now, this is a rational expression, and so you certainly should look and see if it's du over u, but it's not exactly du over u, is it? Because if u is x squared plus 16, du would be 2x, but I've got a 2x plus 3 in the numerator. And so that should give you a hint as to what to do. You do have that 2x up there. And so if you just split this integral into two pieces, so you have 2x over x squared plus 16 dx plus 3 over x squared plus 16 dx. Remember, that's legal to do because you can find antiderivatives term by term like we're doing here. Right? You looked at that in Cal 1. Each of those integrals individually is an easy integral because this first one is exactly in the form du over u. So that one's going to be a logarithm because the derivative of x squared plus 16 is exactly 2x dx. And then the 3 over x squared plus 16, well, the 3 you can bring outside the integral. And so that's just the form for the arctangent. That's exactly in the form a squared plus u squared, du over a squared plus u squared, where a would be 4, u would be x, and du would be dx. Right? U is the expression that's being squared, remember, the function that's being squared, and so that would be x. A squared represents the constant, so a would be 4. Right? A squared is 16, so a is 4. So this matches up with the arctangent exactly. And so we're ready to write down the antiderivative. So the antiderivative for the first term would be the natural log of x squared plus 16, because it's exactly in the form du over u, just like it is. On the next term, the 3 comes down for the ride. It just sits outside the antiderivative. And then you have 1 over a. So this would be 1 over 4. So it's 3 times 1 over 4, arctangent of x over 4 plus c, like that. And you've got it. If you want to write that 3/4, that's fine. So you get 3/4 times arctangent of x over 4 plus c. See, if you had not split that up, you would have been in trouble on this problem, quite likely. And so splitting it up really was an advantage in this problem. All right, so the three things that I wanted to remind you about integration, and there'll probably be another 1 or 2 things on Wednesday of this week also. So over these first few days, I'm going to do a little bit with integration at the beginning of each lecture, just to kind of go back and remind you of some things from Cal 1. Remind you some very important things from Cal 1, by the way. All right, so now we are moving on to area between curves. So let me draw a couple of pictures, and then we're going to look at a couple of problems. So remember what we talked about last time was that if you have 2 functions and you're looking at the area bounded between those 2 curves, so let's say that that's the function f, and this is the function g, is this one in green like this. And there's g right there. And you're trying to find the area between those 2 curves, right? So this area in here is what you're interested in finding. That what I would like you to do is I'd like you to draw in a representative approximating rectangle. I think that's important to do that. So we draw in a rectangle, and that rectangle that I drew in right there has got a nice bound on the top of it and a nice bound on the bottom of it. F always bounds the top of that rectangle. G always bounds the bottom of that rectangle, anywhere in the region we're talking about. And so a vertical rectangle would be appropriate here. And when you draw a vertical rectangle, the width of that rectangle, remember, is dx. And basically, remember that rectangle right there, right? Its width is dx, and its height, this distance right here, is simply the upper curve minus the lower curve, f minus g. And so the dimensions of that rectangle are f minus g dx. And so that gives you, you can always think about it that way to get the area. And so the area in a problem like this, or in a picture like this, you would need the points of intersection of the 2 curves. So let's say that this point of intersection is AB, and this point of intersection is CD, and you're not always going to be given that. But if those are the points of intersection, then the area of that region would be the integral from x equals a to x equals c. Those are the x values of those 2 points of intersection. And remember, this is always going to be the upper curve minus the lower curve. So this is going to be f of x minus g of x dx, like that. Okay, so, and again, let me write out in words that that's the upper curve minus the lower curve. All right, now sometimes drawing in a vertical rectangle doesn't really, it's a more complicated situation if you do that. So for example, in a problem like this, let's say that I've got my curves. I have this line like this, and let's call that, let's say that we've got that curve is a function of y instead of a function of x. That we have x equals some function of y right there. And then we have another curve. Let's say like this right here. And this is x equals some other function of y. Let's call it g of y. And we're trying to find the area bounded between, let's say, maybe like this, y equals a and y equals b, like that. Right? So those horizontal lines right there look like that. Let me clean that up just a little bit. Look like that, and the area, the region we're talking about, or the region we're talking about, is this region like this. Right, that's what we're trying to find the area of. So a vertical rectangle doesn't make any sense because it depends on where you draw the vertical rectangle as to what the bounds on the rectangle are. You draw it in different places and you've got different bounds, all sorts of different ways that works in that particular picture. But if you use a horizontal rectangle instead, like this, then all of a sudden you've got a situation where the bounds, when that doesn't look like a rectangle at all, does it? So let me try it again. Maybe a little bit more like a rectangle. And so that particular rectangle always has the same bounds, right? The right bound on that rectangle is always g of y, and the left bound of that rectangle is always f of y. All right, so since it's got the same bounds, this is a much easier situation. When you're using a horizontal rectangle like this one, then this distance is a change in y, and that's dy right there. And then this distance right here would be the right curve minus the left curve. So this would be g minus f right here. And the area would be g minus f dy. Right? The important thing is that the width of that rectangle is dy, and that's telling you integrate with respect to y in this problem. And so the area for this particular region would be the integral from y equals a to y equals b. So the limits of integration are now y values, and that rectangle varies from y equals a to y equals b. And this would be g of y minus f of y dy, right? And that would represent the right curve minus the left curve. All right, so these two pictures are illustrating this idea that if you've got, and this is important, that if you're using a vertical rectangle, well, okay, so vertical rectangle, then you are integrating with respect to x, and the limits of integration need to be x values. On the other hand, if you're using a horizontal rectangle in the region, then you are going to use dy, right? And you're going to integrate with respect to y. All right, so you kind of have to make a decision about what kind of picture you've got in the problem. All right, so with all that kind of a setup in mind, let's look at some examples here of some problems where we're talking about the area between two curves. So, and again, shout out if you have a question. So the example here is find the area bounded by f of x equals x squared and f of x equals 6 minus x. All right, so the first thing you need is you need a picture, and you need to know where the points of intersection of these two curves are. Now, sometimes if you just sketch the graphs, the points of intersection are going to be obvious from the graph. But let's look at this algebraically in case that was a situation where you couldn't do that. And so the points of intersection, you know, you've got y equals x squared and you've got y equals 6 minus x. So you're just using substitution, and you're literally just setting the two expressions equal to each other to see where they intersect. So you got x squared equals 6 minus x. And so that's a quadratic. And you could solve that easily by setting it equal to 0 and factoring. It's an easy factoring problem. And you end up with x equals -3 and x equals +2. Now, you could use y equals 6 minus x to find the y values there. And when x is -3, y is 9. And when x is 2, y would be 4. So the 2 points of intersection are at -3, 9 and at 2, 4. All right. So let's see what's going on here, how this is going to look. So I'm going to draw a picture here. I'm going to make sure I can get -3, 9 on there. And be able to get both of these sketches, or both of these graphs on the picture here. So let's see, -3, 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9. So -3, 9 is way up here. And then the point 2, 4, 1, 2, 3, 4 is right here. So I know that, and for some reason I called the two functions both f, and I just realized that just now. So let's call the second function g. Let me change that, because we definitely wouldn't be naming them the same thing. So g is just a line. And so here's my line. All right, so there's my function g. And then f of x equals x squared, we know is a parabola that has a vertex at the origin. So that graph looks like this. And we also know the 2 points of intersection. So we know that this graph let's see, kind of goes like this. And so like this. Right? And so the region we're talking about finding the area of is this region in here that I'm going to shade. Right? That's the area that's bounded between these two curves. All right, and so this problem, if we draw a representative rectangle in here, this looks pretty clear cut, right? That we're going to integrate with respect to x. This rectangle, as it sweeps from left to right across that region, always has the same bounds on the top and the bottom. And so the area of this region would be the integral from, now remember, this point is at -3, 9, and this point is at 2, 4. And so we're going to integrate. We use the x values of those 2 points. And so this would be -3 to 2. And you'd have the upper curve, which is 6 minus x. And then the lower curve, which is x squared. Upper curve minus lower curve, dx, like that. Right? It's always upper curve minus lower curve, remember, in that region. All right, so I put parentheses around those two functions, though I really didn't need to do that in this particular problem. Sometimes you will, because you have to pay attention to the signs of the function. So you have a pretty easy integral. You just have the integral from -3 to 2 of 6 minus x squared. And so write down the antiderivative, which would be 6x minus 1/2 x squared minus 1/3 x cubed. And that would go from -3 to 2, like that. Right, and then you evaluate it. You're using the fundamental theorem of calculus here and putting in the upper limit. And then minus, and then putting in the lower limit. Like this. Like so. Right, and then what I'm going to do here is I'm not going to finish this arithmetic here, definitely. This is arithmetic from here. I'm just going to say this is 12. 1/2 times 4 is 2. 2 cubed is 8, so this is minus 8/3. And then you're subtracting, and this is -18. And then you've got -3 squared, which is 9, so this is minus 9/2. And then -3 cubed is -27. Times -1/3 is positive 9. Right, like that. And then all I'm going to say here at the end is I'm going to put dot, dot, dot. I'm going to put etc., etc. Right, you finish that arithmetic at home. Now do kind of think about whether your answer makes sense. Remember, you're finding the area of that region. And so, if you got 5,362 as an answer, that's going to be wrong because, if you think about it for a second, if you look at the picture, this little square that I'm putting in blue right here has an area of 1 square unit. So there's not that many square units inside there, right? And so think about what kind of an answer makes sense. Also think about the fact that the answer has to be positive. That if you get a negative answer, frequently what that means is that you subtracted the curves in the wrong order. When you get the wrong sign on your answer. But think about whether your answer at the end makes sense. A lot of times you can find that you've made a mistake by just thinking about whether the answer makes sense in the context of the picture that you have. So, all right, so everybody's okay? I don't hear any questions at all. Okay, so then we are going to continue on. We're moving along. And so the next problem is find the area bounded by x equals 4 minus y squared and x equals y minus 2. All right, those two equations. All right, excuse me. So again, you need a picture and you need to find the points of intersection. You also know one of these graphs is a parabola. It's a parabola that opens to the side because it's a y squared. The other one is linear. The points of intersection, just like on the last problem, except now we're solving for y first. Other than that, it's basically the same. So you have y minus 2 equals 4 minus y squared. All right, so you solve this for y. You add y squared to both sides, then plus y, subtract 4, and you get y squared plus y minus 6 equals 0. And so that factors y plus 3 times y minus 2, and that gives you y equals -3 and y equals +2. So when y is equal to -3, if you use x equals y minus 2, then x is going to be equal to 4. You've got the point of intersections at -5, -3. Yeah, and so I have the graph sketched wrong. And so the intersection points at -5, -3. Okay, that was kind of ridiculous. And so this is not the right graph right here, this red graph. Yeah, that just goes to show you when you're not paying attention, you can make careless mistakes. So, And I certainly was doing that. So 1, 2, 3, 4, 5, -3 down here. So that's better. And so here's my graph. That's much better. And here is the graph of the parabola. And so we've got this, this region is the region I'm talking about trying to find the area of. Okay. Now I feel better. And making a simple arithmetic mistake there. And this is a classic example where it would not make any sense, excuse me, to use a vertical rectangle. You have to use a horizontal rectangle. And so when I use a horizontal rectangle like this, it means I'm integrating with respect to y. And this is going to be right curve minus left curve. And so the area is going to be the integral from, excuse me, remember now, now you're using y values. So this is going to go from -3 to 2, like this. And it's going to be right curve minus left curve. And so it'd be the parabola 4 minus y squared minus the linear function y minus 2 dy, like that. All right. And so then you go through and I would distribute the minus sign through like that. And then kind of collect like terms. Simplify this thing as much as you can before you actually find the antiderivative. So you have -y squared minus y plus 6, like that. And then when you go ahead and find the antiderivative using the fundamental theorem, you've got -1/3 y cubed minus 1/2 y squared plus 6y, and that would go from -3 to 2. And this is another example where at this point, I'm going to let you finish the arithmetic. At the upper limit, you've got 2 cubed in there, minus 1/2 times 2 squared plus 6 times 2. This is very similar to the last problem as far as the kind of arithmetic that you've got. And you just have to be careful here that you don't make a careless mistake like I was doing originally on the graph. And then you kind of get off on the tangent and then you never can kind of break out of it. So I'm going to put etc. here, ... and you finish up the arithmetic on that problem. All right. So I want to leave that problem behind, definitely. And so now we're going to go on and look at one last area problem. And let's see if I can get this one right as far as the picture goes right away. We're going to try to find the area that's bounded by the curves y equals 12 minus x, y equals the square root of x, and y equals 1. In fact, this is a problem that's in your textbook, and it's one of the practice problems that I assigned out of section 2.1. All right, so let's just look at the graphs on these two functions, or these functions here. So you've got y equals 12. So the intercept is way up there at 12. And so I'm going to kind of stretch this out a little bit like this. And 12 minus x, when x is 0, y would be 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is way up here. And so that's our x-intercept. And that's the y-intercept. And then the x-intercept, when x is 12, y would be 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is right here. And so here's the line, like this. All right, so there's 12 minus x. And then y equals the square root of x. Well, y equals the square root of x. We know what that graph looks like. It starts at 0, 0 here, and then goes through 1, 1, and then 4, 2. And then the next point would be at 9, 3, 5, 6, 7, 8, 9, 3. And notice we're getting from the graph that that these two curves are going to intersect at this point 9, 3. Just by sketching the two graphs, we can see that that's what's going to happen. And then finally, you have y equals 1. You have a third curve in here. And the third curve is this horizontal line, y equals 1, like that. All right, and so notice you've got the region that's bounded by these three graphs is this region in here. So this is a region that is going to require a couple of steps to accomplish this integral if we're going to use a vertical rectangle. Now, if you use a horizontal rectangle, you could actually do this with one integral, but with a vertical rectangle, you're actually going to need two rectangles to do this. In other words, two integrals. So if you're using vertical rectangles, you're going to have to draw, if you draw that rectangle right there, square root of x bounds it on the top and y equals 1 bounds it on the bottom. If you draw this rectangle right here, then the line 12 minus x bounds it on top and y equals 1 bounds it on the bottom. So if you're going to use vertical rectangles, you would have to use two integrals here. So I'm going to write that up here. So using vertical rectangles, the area in this particular problem would be the integral from this point of intersection, which is at 1, 1. This point of intersection is at 9, 3, so that's when x is equal to 9 right there. And then finally, this point of intersection right here is at 11, 1. Like that. And so we would have to integrate from 1 to 9, first of all. And it would be upper curve minus lower curve, and it would be the square root of x minus 1, which is not a hard integral, but that's what you'd have to write out. And then you'd have to add to that the integral from 9 to 11. And then the upper curve would be 12 minus x, and the lower curve would be 1. Now, like I said, this is not a hard problem, not as far as doing it this way, and these are not difficult integrals at all. The area on the first one, this would be the integral from 1 to 9 of x to the 1/2 minus 1 dx. The second integral would be the integral from 9 to 11 of 11 minus x. So neither of those is difficult at all. And the area would be 2/3 x to the 3/2 minus x. That would go from 1 to 9. And then that would be plus 11x minus 1/2 x squared from 9 to 11. Right? And then you'd have to go ahead and evaluate that, which wouldn't be too terribly difficult to do. It's actually not as probably as messy as some of the ones we've just been doing. So when you put in the upper limit for that first integral, let's see, I'm going to continue that underneath here. You got area equals 2/3 times 9 to the 3/2 minus 9 minus the lower limit, which would just be 2/3 minus 1. And then that would be plus, on the second integral, you'd have, putting in 11, you get 121 minus 121/2 minus, and then in the lower limit, you'd have 99 minus 81/2. Yuck. So that would be the arithmetic for doing this with vertical rectangles. And then area equals, and then dot, dot, dot right there. Now, with horizontal rectangles, you could actually do this problem just with one integral. And the reason why is because if you look at this horizontal rectangle, no matter where you draw it, you always have the same curves bounding the right part of that rectangle and the left part of that rectangle. And so you could actually just get by with one integral here with horizontal rectangles. Now you would have to write the curve that y equals the square root of x. You'd have to make sure that you wrote that, solved it for x, so you'd have y squared equals x. And then the red graph where you've got y equals 12 minus x, you'd have to solve that one also and write it correctly. So let's see, you've got y equals 12 minus x, and you'd have to solve that one for x. So you'd add x and subtract 12, and so you'd have x equals 12 minus y, and that would be the right bound on that rectangle. It actually would be a much easier way to do the problem if you were paying attention to it that way. And so the area here would be the integral from y equals 1 to y equals 3 of the right curve, which would be 12 minus y, minus the left curve, which would be y squared. It's actually a much easier integral, dy, than we got originally. And then you finish that problem. You're going to get the same answer either way. So you could compare your answers here, but you should get the same answer for both of these approaches to this problem. And so I'm going to put area equals, and I'm just going to put same answer here. So notice, depending on how you looked at this problem, you could have used two vertical rectangles. That would have given you two integrals with respect to x. Or you could have used one horizontal rectangle, which would have given you one integral with respect to y. So it's probably a good problem to look at for those reasons. All right. Now I've gone through that. I don't know if you guys are still with me or not, but hopefully you are. And so let's go ahead, and that's going to finish our discussion of area between two curves. You've got homework problems definitely that I want you to look at for area between two curves, so be working on that. What I'm going to do next is I'm going to move on to volume using discs. And technically volume using discs and washers. Now, the kind of figure we're talking about here is we are talking about volumes of surfaces of revolution, or solids of revolution. Volumes of solids of revolution. And so, first of all, we want to talk about what a solid of revolution is. So we're going to look at I'm going to show you a animation of a volume of a solid of revolution, what a solid of revolution is, and then we're going to actually go ahead and look at this video here, and you can see what a solid of revolution is. So in this problem, we're looking at the function y equals the square root of x. And so you graph y equals the square root of x, that curve right there. And then we're looking at the curve y equals 1/10 x, which is a linear function that goes through the origin, goes off to the right, and they are going to, and then x equals 4, which is a vertical line right there. And so we're going to take that region that they just shaded, and then we're going to rotate it around the x-axis. And when we rotate it around the x-axis, notice what you get is you get a solid of revolution. And this is a solid of revolution with a hole in it. That disc that they're rotating right there is called a washer because it has a hole in it. All a washer is really just a disc with a hole. All right? And so that's what they're kind of illustrating with that particular video. All right, so I wanted to show you that video. Next video I want you to see is a similar kind of picture here. This is by Ellen Turnell from our math department, where you have a solid of revolution, like I just showed you, what we were just illustrating right there, where we're taking the region y equals the square root of x and the x-axis and rotating it around the x-axis there. And so we get that solid right there. And we're going to identify a rectangle inside that solid. And that rectangle generates a disk. And that disk is what's shaded in blue there in the middle. The width of that disk is dx. And that that disk is really, if you think about it, it's kind of like that this is a very flat cylinder. And so we think of that dx as actually being the height of that cylinder, where that cylinder is actually lying on its side. This would be another example of a solid of revolution that we're talking about. All right, we're taking the curve y equals 2 times the square root of x and rotating it around the y-axis in this case. All right, so I definitely wanted to just show you a couple of animations of what a solid of revolution is. And so now we're going to take the time to actually draw some stuff out and actually see what we can figure out about finding these volumes. All right, so I'm going to start off with a problem that's actually kind of easier than both of those pictures, probably in general. This is the function y equals 4 minus x squared in the first quadrant. So we're going to take that region, just y equals 4 minus x squared, the region in the first quadrant that curve kind of delineates, and we're going to rotate around the x-axis to generate a solid of revolution. And what we're going to try to do is we're going to try to find the volume of that solid of revolution. All right, so that region, I'm going to draw a couple of pictures here. First of all, it's a parabola that opens down, right? And so what I'm going to do is I'm going to kind of blow this up a little bit so that we can maybe see things a little bit better. So there's my scale, and the vertex is up here at 0, 4, and the x-intercept is over here at, let's see, there's 1 and there's 2, and that's at 2 right there. And so we're talking about this region like this. Right, and what we're going to do is we're going to rotate that region around the x-axis, okay? So this is the region we're talking about right here. I'm going to shade it. And then we're going to take that region and rotate it around the x-axis to generate a solid. All right, so when we do that, what you get, let's see, I'm going to continue this picture on like this. So 1, 2, 3, 4. You get this cross section like this. And that's kind of a cross-sectional view of the solid that we're talking about. And what we're going to do is we're going to rotate that around, like I said, we're going to rotate around the x-axis. All right, so when we rotate that solid around the x-axis, you're generating this solid. It's kind of like a Hershey's Kiss that's been melted a little bit, would be one way to say it. That's also kind of on its side. When we draw in a representative rectangle in this region like this, what's going to happen? This rectangle is going to have a cross-section over here, down below the x-axis as we rotate. And that, as we rotate around, we're actually generating a disk. And I'm going to actually draw that disk over to the side over here, like this. And so that disk, and here's our cross-section of it. And so you've got this disk that's, and here's the x-axis coming out from this. And here's kind of the back part of that disk like this. And so this is our disk that we're generating like this. And here's the x-axis coming out from that disk. I'm going to draw it right here. Right, and so that's a very flat disk. That's what it is a flat cylinder. It's a very flat cylinder. It's a very flat circular cylinder. And the volume for a cylinder, for a circular cylinder, is pi r squared times the height of that cylinder. Well, the height of the cylinder, remember this is a very flat cylinder kind of lying on its side, And so the height of that cylinder is the width of that rectangle, and so that would be dx. And then the radius of that circular cylinder is this distance right here, like that. And if you look back over to our picture, that's this distance right here is the radius. That's r, and that would be our function, and so that would be y equals 4 minus x squared. That's y, which is 4 minus x squared. Right? That's a y value right there. And so what do we have here? That the volume for that disk would be pi times the square of the radius, but the radius is 4 minus x squared, and then that would be times the height, which is dx. And what we're kind of doing is talking about what we call the disk method right here. The disk method, the general form for the disk method is that the volume is given by this integral, pi times the square of the radius dx, or depending on how you're drawing the rectangle, it could be pi times the square of the radius dy. Right, depending on the picture that you've got, whether you're dealing with a vertical rectangle or a horizontal rectangle. And that's the kind of the general idea behind the disk method. So now in our particular problem, if you think about this, we could actually kind of squeeze in this calculus off to the side here. The volume is going to be the integral from, the x value varies from 0 to 2, and this would be pi times the square of the radius, which would be 4 minus x squared dx, like that. And so that's our integral for this particular, the volume of this particular solid of revolution. So you have pi times 16 minus 8x squared plus x to the fourth dx. And then you can kind of continue on with that integral right there, right? And again, it's kind of a it's a polynomial. It's not too bad of an integral. It's just messy at the end here. You have pi. You can take the pi out since it's a constant, and this would be the integral from 0 to 2 of 16 minus 8x squared plus x to the fourth dx, like that. And then you could go ahead and find the antiderivative there, which is 16x minus 8/3 x cubed plus 1/5 x to the fifth. And that would go from 0 to 2, like that. Luckily, at 0, everything is 0. And so all you're doing is substituting in 2 here. And so you have pi times 32 minus 64/3, if you're doing the arithmetic there, plus 32/5. Right, and then again, you could finish that arithmetic up, and I'll put dot, dot, dot there. It's pi times something over 15, and then you're going to go back through the arithmetic. So the idea here is that you're going to use this form for the disk method, where you're generating or using a rectangle to generate a disk, and then you're writing down the expression that gives you the volume of that disk. Now, what happens is, okay, so that's a good example right there to start off with. Now, before we do anything else, let's just look at maybe one more problem like that. So let's say we have, and this is going to be kind of a simple example, a relatively simple example. Let's say we have f of x equals 4 minus x. Just look at a linear function here. All right, so, and let's look at the region in the first quadrant again. And let's rotate around the x-axis. All right, so that particular solid you have y equals 4 minus x. And I tell you what I'm going to do is I'm going to actually change this I'm going to change it to a different function rather than that one. I think this will be better for us. Let's say that f of x is equal to just x. I'm going to make it even easier than that. And we're also going to look at the function x equals, or the line x equals 4. I think that's going to work out better for us. So x equals 4 is this vertical line right here. Here's x equals 4. And here's f of x equals x. Like that. So this is the region we're rotating around the x-axis, just this triangle. Okay, so when we rotate around the x-axis, we're going to identify a representative rectangle and an approximating rectangle inside there, and we're rotating that rectangle around the x-axis. So you know the cross-section in this case, if you're looking at the solid that you're generating, that's the cross-sectional piece right there. And you've got this piece like this, and you're rotating around the x-axis. So you're getting, let's see, yeah, use red there. So you're getting a solid that kind of has an end, if you're looking at it as an angle, kind of a circular end to it like that. Like so. And let me go ahead and extend this blue line here, make it look a little bit more decent. Right, and so that would be kind of our solid here. And so when we rotate that representative rectangle, here's the rectangle that we're rotating, right? And what are we doing? We're generating a solid again, a solid disk. And I'm drawing that disk off to the side over here. This is the disk we're generating. Like this. Right, and that's the disk that we're generating off to the side over there. And so the volume, what I would always do here is I'd write down volume is pi r squared times the height. So in our problem, the radius is just the function value, right? This is the radius right here. The radius of that rotation is this distance right here. It's always going to be from the axis of rotation out to the end of that rectangle like that. And so that would be given by y. And y is equal to x in this case, right? Because you're talking about the function f of x equals x. So our volume in this case, if you write the integral out, first of all is going to be pi r squared dx, because h is dx. And r in this problem is going to be equal to y, which is equal to x. And so the volume would be the integral from 0 to 4 of pi x squared dx. Pretty simple integral. And so you end up with, let's see, you end up with pi over 3 x cubed from 0 to 4, or just 64 pi over 3. All right, now, so a couple of things here as we're approaching 8:30. One thing is that what we have left to do this week then on Wednesday, so that's a couple of examples of the disk method there. So on Wednesday, we're going to look at the disk method with a hole in the disk. That's generated. This is sometimes called the washer method. So when you generate a hole, when you're rotating that rectangle around the x-axis or the y-axis, you just call this the washer method. And then we'll also look at rotations around the y-axis and other lines. So the first two problems we looked at were rotations around the x-axis. And then we will also look at the shell method. The shell method is a different way of finding the same kinds of volumes. All right, so those are the two things that we'll do next time. So we'll finish the disk method, and then we'll do the shell method. All right, so now the homework that I'm going to assign. So these are problems that are due on January 28th. And so these are out of your textbook. And so this is on page 153 of your book. Page 153, I want you to look at problem number 76. Right, that's a volume problem where with the disk method. And then also I want you to look at, and this is out of section 2.1, for an area between two curves. I would like you to simply turn in, this is on page 133 of your book, problem number 2. All right, so those two problems, and then on Wednesday I'm going to assign a third problem, and those are going to be due on Wednesday. Now I do have a question here. So I did get a question from somebody by chat on here. Sang asked me a question about the format for the exams. The exam format is paper and pencil. So very traditional as far as the way the tests are going to look. So you do not have to bring paper or anything. The testing center will supply you with the test, and you'll complete the exam on the test itself. I'll give you room to work the test on the paper itself, and then you'll just turn in that work and your scratch work, whatever scratch work you have, to the testing center. And then they will scan that and send it to me. So Sang, is that okay? Does that make sense? Is that as far as my answer to your question? Okay, very good. And Jaime, do you have any questions at all?
No.
Okay, so practice this. I know we've only gotten through 2 disk method problems, but start working on that, and then we'll work more on disk method going into Wednesday. And for any of you that are watching live or online, live or recorded version later, please don't hesitate to come by my office for help or email me a question. And I have no problems answering questions by email. Okay, so everybody have a great evening, and I will talk to you on Wednesday, if not before.